Hello students, functions maths 1b first chapter theorem 1. Let f maps A to B, G maps B to C be injections. Then G circle f maps A to C is also an injection. Okay, take given f from A to B, G from B to C are injections. We have to prove that G circle f maps A to C is also an injection. I explained all the definitions 1 and on to bisection and types of functions in the previous video. You can watch. Okay, we are going to prove G circle f maps A to C is an injection. So for that we have to take two elements in the domain. A is the domain and C is the codomain. So in A first set means in the domain we have to take two elements. So in capital A we are taking small a, A1, A2, two elements we have to take. So let A1 comma A2 belongs to A, and also have to take G circle F maps G circle F of A1 equal to G circle F of A2. Okay, to prove 1 function or injection we have to take two elements in the first set, that is domain, and we have to take G circle F of A1 equal to G circle F of A2. Okay, then G circle F of A1 can be written as G of F of A1 equal to G of F of A2. Okay, it is f of A1 equal to f of A2 because G is removed here because it is 1, 1. So given G maps B to C is 1, 1. So we can write G of f of A1 as f of A1. So the reason, since G maps B to C is 1, 1. That is injection. So both sides CF also can be removed. A1 equal to A2, since the reason is F maps A to B is 1, 1. F maps A to B is 1, 1. That is injection. Then we have taken G circle F of A1 equal to G circle F of A2. Then the answer is A1 equal to A2. Then this G circle F is 1, 1. Therefore, G circle F maps A to C is an injection. Hence proved. Okay, the second theorem is let F maps A to B, G maps B to C be surjections onto. Surjection is onto function. Then G circle F maps A to C is also a surjection. The second theorem is let F maps A to B, G maps B to B surjections. Then G circle F maps A to C is also a surjection. Given F maps A to B, G maps B to C are surjections, we have to prove that G circle F maps A to C is also a surjection. So here surjection means it is an onto function. We have to define these two functions are onto functions. So first take the second function. Since G maps B to C is a surjection, so function definition of surjection or onto function is we have to take one element in the second set codomain, then there exists an element in the first set, that is in the domain, then G of B equal to C. Okay, we are taking small c in the second set, then there exists a small b in the second set, then such that G of B equal to C. This is the definition of onto function. Okay, then for second set, take an element in the second set. Small c belongs to capital C. Then there exists one element in the first set, that is in the domain B belongs to capital B, such that G of B equal to C. Okay, let it be equation 1. Okay, one more function is onto function. F maps A to B is also an onto function. So write the definition. Since F maps A to B is a surjection, can also write onto. So for small b belongs to, take the element in the second set codomain, So for small b belongs to capital B, there exists small a belongs to capital A such that f of a equal to b. F of a equal to b. This is second equation. Okay, we have to prove that G circle F maps A to C is a surjection. So for that, an element C belongs to C. There exists small a belongs to A such that G circle F of A equal to C. Okay, we have to prove G circle F of A equal to C. So taking an element A belongs to first set. So let small a belongs to capital A, G circle F of A, okay, equal to B. We have to prove G circle F of A equal to, G circle F of A equal to C. Okay. G circle can be written as G of F of A, and F of A is B from the second equation. Okay, by the second equation it is equal to G of B, and G of B equal to C from the first equation. So by the first equation. Okay, G circle F of A equal to C. Okay, therefore for C belongs to C, there exists small a belongs to capital A such that G circle F of A equal to C. Hence proved. Next theorem number 3. Let F maps A to B, G maps B to C be bisections. Then G circle F maps A to C is also a bisection. So bisection means a function which is both on one and on two. So this is a consequence of first theorem and second theorem. So we have to write the proofs of first theorem and second theorem. Next theorem number 4. Let F maps A to B, G maps B to C be bisections. Then G circle F inverse equal to F inverse circle G inverse. Okay, in this type of proofs we have three different parts. Okay, the first part is left hand side function and right hand side function both have the same domain and codomain. The second thing, writing the onto definition and inverse. And the third thing, if you take any element in the first left hand side function, the same element should be present in the right hand side. These are the three things to prove. You can remember easily by using these three steps. The first one, same domain and codomain. Second one, onto and inverse definitions. Third one, same element. Okay, the first part, F maps A to B, G maps B to C are bijections. Then G circle F maps A to C. G circle F maps A to C is also a bijection. If you take the inverse of this, G circle F whole inverse maps, this is in reverse order, C to A. It is also a bijection. Okay, let it be equation 1. Given F maps A to B, G maps B to C are bisections. Okay, how to write in this order? G circle F maps A to C. Okay, the first function codomain, second function domain must be same while writing in this case. So G circle F maps A to C is a bisection. And you can write inverse function. G circle F whole inverse maps C to A is also a bisection. This is the first equation. Left hand side function, its domain is C and codomain is A. Now the right hand side function F inverse circle G inverse. So first you have to write about second thing, G inverse. We know that G maps B to C, then G inverse maps C to B. And F inverse maps B to A are bijections. Then F inverse circle G inverse maps C to A is also a bisection. Let it be the second equation. Therefore, from 1 and 2, G circle F whole inverse, it has domain C and codomain A, and the second function is also contains domain is C and codomain is A. So from 1 and 2 we can write 1 and 2 left side G circle F whole inverse and right side function, that is F inverse circle G inverse, have same domain and codomain. So the first part is completed, and the second part is definition of onto, and also have to write inverse. Okay, here two functions are bisections. The two functions are bisections. F and G are bisections. Bisections means 1, 1 and onto. So you are writing the definition of onto function. So to write the onto function, we have to select the second thing first. So G maps B to C is onto. Since, so the second part, since G maps B to C is onto R surjection, then the definition for onto function is take an element in the second set, then there exists an element in the first set such that G of B equal to C. So for C belongs to capital C, then there exists one element B belongs to capital B such that G of B equal to C. Okay, at the same time we can write inverse function for this. So the inverse G of B equal to C, then G inverse of C equal to B. Okay, let it be equation 3 and this is 4. Okay, F is also onto. Since F maps A to B is onto, so take an element small b belongs to capital B, there exists small a belongs to capital A such that F of A equal to B. Let it be fifth equation and write the inverse part. F inverse of B equal to A. This is the sixth equation. So the second part is also completed. Now the third part is same element. Same element, left side LHS and RHS contains the same element. So the third part, okay, since G circle F from A to C is a bisection, so bisection means 1, 1 on 2, so we can write G circle F of A equal to C. So directly we are taking G circle F of A equal to C. Then you can write the inverse part of this. G circle F whole inverse of C equal to A. Okay, from the sixth equation, A can be written as F inverse of B. Okay, F inverse of B can be written as F of A or G inverse of C. But here G inverse of C is useful. So B, in the place of B, you can just write G inverse of C. Okay, this is from the fourth equation. From the fourth equation, B is G inverse of C. Then you can write F inverse circle G inverse of C. So we can write F inverse circle G inverse of C. Okay, then left side we have taken G circle F whole inverse of C. Here we got F inverse circle G inverse of C. So it contains the same element. So LHS contains C and RHS also contains C. So the same element. Therefore G circle F whole inverse equal to F inverse circle G inverse. Hence proved.